I'm going to tell you how magnets work. We're going to start with the idea of an electric charge. There are two kinds, positive and negative. They attract one another. Opposite charges attract. This is the electric force. But physicists prefer a more abstract way of describing the electric force. We use the idea of a field to describe these forces. So let's go back to looking at a single charge. We imagine that an electric charge affects the space around it by emanating an electric field. An electric charge produces an electric field. The electric field is used to describe the force felt by another charge. So if we now bring our negative charge in the picture, we can describe the force it feels through an interaction with the electric field. Okay, so a magnetic field is described similarly, so I'm just giving you that background. So now we're going to move on and we're going to look at electric current. Okay, so let's put our charges inside a battery, one at the positive terminal and the negative charge at the negative terminal, and we're going to connect the two battery terminals with a wire. The charges are going to move along the wire. This is what we call electric current. And here's the thing about electric current. A current produces a magnetic field in a way that's analogous to how an electric charge produces an electric field. The geometry of a magnetic field is not as straightforward as the geometry of the electric field, so I haven't drawn it here. But if we configure the wire into a loop, then a uniform magnetic field will form through the center of the loop, and I can draw that. So you can add more loops to your wire to make the field stronger. And this is an electromagnet. An electric current, so in summary, an electric current produces a magnetic field. And the magnetic field produced by this coil geometry in particular looks like that of a bar magnet. And so here's the next question. I've told you an electric current is what produces a magnetic field. So where is the current in a bar magnet? So to get at this, we need to think microscopically. Matter is made up of atoms, and atoms contain charges, and those charges move around. Remember, a current is really just a moving charge. That's what current is, moving charges. And current produces magnetic fields. So this is a Bohr model of the atom, which isn't accurate, but it lays out all the right parts. Atoms contain protons and neutrons at the nucleus and electrons in orbitals around the nucleus. Protons are positively charged and electrons are negatively charged. These particles have some pretty complicated dynamics within the atom, which I won't get into, but it suffices to say that their motion gives rise to a magnetic moment. So you can think of each atom as a tiny little magnet. Now, in most materials, these little magnets are pointing in all kinds of different random directions, so they all cancel each other out. And most materials are not magnetic. But in some materials, all the magnetic moments from each atom align with one another. These are called ferromagnetic materials. And that's how we get magnets. So yeah, to recap, electric charges produce electric fields. Electric fields describe the force felt by a charge. Electric current produces a magnetic field, and the magnetic field describes the force felt by a nearby magnet or the force felt by a wire that is carrying current, right? Remember, a wire that is carrying current is pretty much a magnet. It's an electromagnet. So this is actually the basic principle behind electric motors. This is a picture I pulled off the internet showing a basic motor. There's a battery, which supplies a current through a loop of wire, and there is a magnet, which produces a magnetic field that exerts a force on the wire. If we put everything in the right geometry, that force is going to make that loop of wire spin. I filmed a little demonstration of a simple motor that you can look up and you can look at it. You can click to it in this link right here that I've put in this video. Cool. Well, thank you.